Magnetic resonance imaging, or MRI for short, is one of the forms of medical imaging commonly used in diagnostics today. It is used when the area of interest is made up of soft tissue, as the chemicals that are responsible for the signals measured, which are lipids as well as water, are most abundant in them. This video will focus on the physics behind how nuclear magnetic resonance, or NMR, is used to generate images through MRI. As a disclaimer, this is going to be a very maths-dense video, so we'll pace ourselves for clarity. Let's get into it. The root of NMR is the interaction of a nucleus with an external magnetic field, and the root of a nucleus's electromagnetic properties is the proton. The proton can be classically modelled as a rotating sphere with mass of 1 atomic mass unit and charge of 1 positive electron charge. This system itself is equivalent to a point charge, like an electron, with the same mass and charge, orbiting in a circular orbit at a velocity v at the radius of a proton. This, in turn, can be thought of as a loop carrying a current made up of just that point charge, like a wire with only 1 electron moving in it. We can now use Ampere's law to see that the proton has magnetic dipole moment, mu. Let's find mu. From the right-hand grip rule, the direction is along the axis of rotation. The magnitude of mu is the current over the loop times the area over the loop. If we define tau as the time for one orbit to be completed, we can use the definitions of velocity and current to write the velocity as the circumference of the circle divided by tau, and the current as the proton's charge over tau. Rearranging to remove tau, we get I equals EV over 2 pi r. We can combine these to get mu equals EVR by 2. We can also say that the spinning sphere has angular momentum, J. The direction of J is also found by the right-hand grip rule, meaning it points along the axis as well. Angular momentum is found from the cross product of the radius and the linear momentum of the particle. We can take a scalar factor, like mass, outside of the cross product, and now we see that J is mass times the cross product of r and v. Since we have circular motion, r and v are always perpendicular, meaning the magnitude of the cross product is equal to the product of the magnitudes. Hence, the magnitude of J equals mrv. One last thing to define that will be useful before we apply a magnetic field is the gyromagnetic ratio, gamma. We define it as mu over J, and as you can see from the animation, this cancels out to E over 2m. We will bring this back up later. Let's now represent the magnetic dipole moment as two magnetic monopoles of equal strength but opposite polarity, plus or minus q respectively, constrained to be separated at a distance d from each other. Now mu in this model is equal to qdn, where n is the unit vector pointing from the south pole to the north pole. It's finally time to apply an external magnetic field, B, at an arbitrary angle theta. The force on the monopoles is plus or minus q, b, respectively. So summing forces, we can see that there is no net force on the system, so there is no translational movement. However, there is a torque on the system. The component of the force perpendicular to the n vector on each monopole is plus or minus qb sine theta respectively. So the total torque on the system is qdb sine theta, which we can see is equal to mu b sine theta. This is the equation for the magnitude of a cross product, so if we represent torque as a vector, we can write T equals mu cross b. We can see from the diagram that direction of T is such that mu and b will tend to align, and this means that the lowest potential energy state is when they are aligned. But suppose there was some kind of unintroduced mechanism that prevents this alignment. What would happen then? Let's start by transforming our torque equation into an equation involving J from the gyromagnetic ratio. Since mu and J are parallel, mu equals gamma J is valid. Let's also consider the rotational counterpart to Newton's second law of dynamics, T equals dJ by dt. If we apply both of these to our torque equation, we get dJ by dt equals gamma J cross B, which tells us that the angular momentum changes in a direction perpendicular to both itself and the external magnetic field. In this picture, it would be out of the screen, towards you. Let's change perspectives to see things more clearly. Now here's the angular momentum and magnetic field vectors at one point in time. When the angular momentum continuously gains dj perpendicular to it over time dt, it moves in circular motion through an angle d phi. From geometry, we can see that d phi equals dj over j sine theta, hence the angular frequency d phi by dt equals 1 over j sine theta dj by dt. Now the scalar dj by dt equals the magnitude of gamma j cross b, which is equal to gamma j b sine theta. So if we substitute that into our equation, we can cancel the j sine thetas out, leaving us with the angular frequency omega naught is equal to gamma b. This means that when the external magnetic field is applied, we get a constant angular frequency corresponding to the circular motion of mu and j vectors about the direction of the magnetic field. This angular frequency is called the Larmor frequency. But what would stop the proton's magnetic moment aligning with the external magnetic field? The answer is quantum mechanics, specifically the uncertainty principle regarding angular momentum. Say we applied the external magnetic field in the z direction, as is convention, and the magnetic moment aligned with the field direction. We would then know that the proton's angular momentum would all be in the z direction, and therefore we would know two components of its spin at the same time. The components in the x and the y direction would both be zero. This is forbidden by quantum mechanics, so they cannot align. In reality, quantum mechanics restricts protons even further by locking them into two states, one at around 54.7 degrees from B, and the other in the opposite direction to that. The reasoning for this, to put it succinctly, is that solving the Schrödinger equation for a spin-half particle with the non-zero potential energy from the magnetic field leads to the solution where the z component of the proton spin is plus or minus h bar by 2, independent of time. We also know that the total spin for a spin-half particle is √3 over 2 h bar, so doing simple trigonometry leads to theta equals r cos 1 over √3, which is roughly 54.7 degrees. This means that all protons will precess at the Larmor frequency when the external magnetic field is applied. Now let's see what happens when we scale it up to a human scale number of protons. When there are multiple magnets close to each other, their fields can be added like vectors to produce a magnetic field net, which from far away is equivalent to one magnet with a field of the same strength of this net magnetic field. Applying this to the protons, if there were a reason for more protons to be in one of the two spin states than the other, then there would be a net magnetic field in the direction corresponding to which state had more protons. As it turns out, there is a reason for the states to be unequal in number. The two states do not have equal energy. The spin down state is at a higher angle to B than the up state, so it has more potential energy. Only slightly more though. This means that there will be a small majority of the protons in the lower energy spin up state, 7 protons per million. This might seem small, but on a human scale, this 7 per million adds up to a non-zero net magnetization vector, which we'll call M. Since the perpendicular component of the magnetic moments of the protons are random at any given time, they effectively cancel each other out, meaning this net magnetization is parallel to the external magnetic field. Now that we have M, let's consider the effect of a second, much smaller magnetic field, B1, on M. Since pointing the second field in any direction with Z components could just be modelled as a larger B0 and a perpendicular B1, let's apply our B1 in the XY plane, along the x-axis for simplicity's sake. When we do, M will begin to precess around the x-axis and move away from the z-axis. As soon as it moves, however, it will no longer be parallel with B0, and thus precess around the z-axis as well, at a rate faster than around the x-axis. This means that before M has gotten very far from the z-axis, it will already have completed a quarter of its cycle around the z-axis, after which its precession around the x-axis will move it towards the z-axis. The total motion of M will be a repeated wobble around the z-axis in the positive x direction. This isn't particularly helpful or noticeable, so let's try something else to get M moving in a useful way. If we rotate B1 at the same frequency that M will precess around the z-axis, i.e. the Larmor frequency, then M will be able to spiral away from the z-axis all the way into the xy plane and below. This behaviour only occurs at the Larmor frequency, and this is the phenomenon named nuclear magnetic resonance. Now let's work on getting an output from this phenomenon. If we place a coil near the protons that is sensitive to changes in the magnetic field in the xy plane, M moving in that plane will induce a small alternating current in the coil. Next, let's apply B1 in a pulse, such that when B1 is removed, M is exactly in the xy plane, so our induced current starts at its maximum amplitude. This maximizes the amount of coherent signal we get before the relaxation mechanisms make M return to being aligned with B0. The signal that we get is a sinusoidal wave of constant frequency, but exponentially decaying amplitude. For just one proton not interacting with anything else, this frequency should be the Larmor frequency. However, chemical conditions such as the molecular structure change the effective magnetic field applied to the proton slightly, according to B effective is equal to B0 times 1 minus sigma, where sigma is a dimensionless shielding constant that depends on the exact conditions the proton is in. This results in a chemical shift in the frequency, defined as the relative change in frequency. This can be different for protons in the same molecule. For example, acetic acid has one of its hydrogen nuclei bonded to an oxygen instead of a carbon, and this changes its chemical shift from around 2 parts per million to a little under 12 parts per million. This chemical shift is a powerful tool for helping build the images, but it doesn't convey any spatial information itself. That's where applying the magnetic field in a way that's variable in space comes in. The magnetic field at a point can be considered as a function of the gradients of each plane along the axis, here written as g with the axis subscript, and the coordinates of the point in space relative to the centre of the magnet. Mathematically, we can write this as b equals b0 plus xgx plus ygy plus zgz, and consequently the precession frequency is gamma times that. We now have spatial information connected to the precession frequency of a proton into its magnetization vector, and consequently the signal output. First is slice selection for the z coordinate. If we make the g's a fixed set of constants, setting b1 to any angular frequency corresponds to a plane in space, usually one perpendicular to the z-axis, since then gx and gy are 0, so that we can set gz and omega, and then work out z from there. This also means we get a pulse from only the nuclei in that plane, getting chemical information only about that specific plane. For a more realistic approach, we usually vary b1 over a small range of frequencies to get a slice with finite thickness. To get different slices, we can either change the gradient of B0 or change the frequency of B1. Next is phase encoding for the y coordinate. Turning off the magnetic gradient in the z direction and turning on the magnetic gradient in the y direction results in the magnetization vector processing along the y-axis at a rate dependent on its y coordinate, meaning that over the time gy is applied, the vector will have rotated by an angle phi dependent on its y value, corresponding to a phase difference in the signal. Finally, for the x-coordinate, we have frequency encoding. Applying gx while measuring data will mean that the signal from each proton will have a different frequency signal coming from it, depending on its x-coordinate. The strength of each frequency signal will depend on the number of nuclei attributed to it, and how much the signal has decayed since the slice was selected. It's also worth noting that, after each of these gradient pulses, the protons in each slice will be slightly out of phase with each other. So to fix this and clean up the signal, after each step, a smaller, negative gradient is briefly applied to get them back in phase again. To make this clearer, here's a diagram of 9 equally spaced protons' magnetic moments at the instant that Gx is applied. It illustrates that the phase of each proton's moments is constant in x and varied in y, and the reverse for the proton's precession speed. All these different frequencies from each nucleus are superposed in the final signal output, and it can be shown that this signal is equivalent to a 2D Fourier transform of a line in the desired image. To get more lines, one can choose a different strength of gy and do the process as many times as desired, typically 128 or 256 times. Then, after applying an inverse Fourier transform on all of those lines, we finally get our desired image. This is the end of the video. We've detailed how to go from a proton's spin up to generating an image from rotating gradient magnetic fields in order to explain the physics behind MRI. A list of references can be found in the description of the video, with square brackets appearing on the screen corresponding to each reference. Thanks for watching this video. The next video will be on proton beam therapy.